Assalamualaikum and very good morning everyone. So today we are presenting about the thickness gauging using radiation. Our group member consists of 4 members which are NURUL ATHIRAH, Nur FATINI, ADNIN and myself Nur ALIF AKMAL.
Assalamualaikum and good morning everyone. My name is NURUL ATHIRAH binti ARMAN. So today we would like to discuss regarding thickness gauging using radiation. So first of all, let us know more about gauges. Gauges is actually an old measures of thickness. They originated in the British iron wire industry at a time when there was no universal unit of thickness. The sizes of the gauges number were the result of the process of wire drawing and the nature of iron as a substance. Gauges were measured and described in fractions of an inch during the 19th century. In the UK, 1 gauge was standardized and legally enforced as the standard wire gauge since it was not an unequivocal unit of length. One important reason for the standardization is because it is for the craftsman convenience. So what is thickness gauging? Thickness gauges are measuring instruments that can be used to determine the thickness or gauge of a material. It is commonly known as a radiation-based thickness gauge or a nuclear thickness gauge. This type of gauge measures the thickness of materials by utilizing the principle of nuclear radiation interaction with matter. There are several different types of thickness gauges, each that function in a slightly different manners depending on the intended application for the gauge. The instrument needed to perform radioactive thickness monitoring is sometimes called a radioactive gauge. Radiation-based thickness gauges offer advantages such as non-contact measurement, fast and continuous measurement, and suitable for various materials, including metals, plastic, and composites. They are commonly used in industries such as steel manufacturing, paper and pulp, plastic and coatings, where precise and non-destructive thickness measurements are required. It is to control the thickness of the product by ensuring that the product or material has the same thickness and coating.
Next, we are going to talk about the fundamental of thickness gauging using radiation. It may sound complex, but don't worry, we'll break it down for you in simple terms. So why is this important? Well, imagine you are working in oil and gas industry and you need to measure the thickness of pipeline to ensure its safety and reliability. Or maybe you are in the manufacturing industry and you need to ensure the quality of your product by measuring their thickness. And this is where the thickness gauging using radiation comes in handy, providing accurate and reliable measurement in a non-destructive way. So what is radiation? Radiation is a form of energy that travels through space and can penetrate various material. It is commonly used in thickness gauging because different material will absorb or scatter radiation differently depending on their thickness. And there are 3 types of radiation commonly used in thickness gauging, which is beta, gamma, and X-ray. Beta radiation consists of fast-moving electron, while the gamma radiation is a type of electromagnetic radiation. And X-ray are also a type of electromagnetic radiation, but with higher frequency than gamma rays. Each type of radiation has its own unique properties and application. Moving on to the types of radiation gauge. There are 3 main types of radiation gauge used for the thickness gauging, which are beta, gamma, and X-ray gauge. Beta gauge uses a radioactive source that emit beta particles, which are high-energy electrons, and this particle penetrate the material being measured and are detected on the other side. And gamma gauge use a radioactive source that emit gamma ray, which are high-energy photon, and these rays also penetrate the material being measured and are detected on the other side. And for the X-ray gauge, it uses an X-ray tube to generate X-ray, which are also high-energy photon, and the X-ray penetrate the material being measured and are detected on the other side. And each type of gauge has its own advantage and disadvantage, and it's suited for the different application. For example, beta gauge are often used for measuring the thickness of plastic film or sheeting, while gamma gauge are commonly used for measuring the thickness of steel or other metals. X-ray gauge are typically used for measuring the thickness of materials that are difficult to penetrate, such as rubber or composite. Regardless of the types of gauge used, thickness gauging using radiation is a critical process in many industries, including manufacturing, aerospace, and construction. And for the theory of thickness gauging, in thickness gauging using radiation, the attenuation of radiation is a key concept. As radiation passes through a material, some of it gets absorbed or scattered. Reducing its intensity and the amount of attenuation depends on the material density and thickness, as well as the type and energy of the radiation used. By measuring the radiation intensity before and after passing through the material, we can calculate its thickness. And the relationship between thickness and radiation intensity follow an exponential decay curve, where the intensity decreases exponentially with increasing thickness. And this relationship is described by the Beer-Lambert law, which states that the attenuation of radiation is proportionally to the material's thickness and density. And by calibrating the gauge with known standard, we can accurately measure the thickness of unknown materials.
Hi, Assalamualaikum everyone. I am ADNIN. So we have go through the fundamental and related theory that explained by ALIF. Radiation-based thickness gauging has widespread application across numerous industries to its ability to provide accurate and reliable measurement of material thickness. This section explores the various industrial sectors where radiation-based gauging is commonly employed. Highly specific application within those sectors discuss the benefits of radiation-based gauging and provides real-world example of successful implementation. Firstly, steel industry. Radiation-based thickness gauge find extensive use in the manufacturing sector, particularly in metal production and processing. They are employed for measuring the thickness of metal sheet, coils, and plates during the manufacturing process. Gauge ensure that product meet precise thickness specification, resulting in high quality end product. For example, to measure the thickness of steel sheets, coil, and plates. These measurements are crucial for quality control, ensuring the compliance with industry standard and customer specification. This enables them to control the thickness within tight tolerance, resulting in improved product quality and reduced material waste. Next, plastic and polymer. Radiation-based gauging is also valuable in plastic and polymer industry. It enables manufacturers to accurately measure the thickness of plastic films, sheets, and extrusion. This information is crucial for ensuring product quality, consistency, and meeting customer requirement. This allows them to achieve consistent thickness across the entire roll, leading to improved product performance and reduce customer complaint. Lastly, paper and packaging. The paper and packaging industry benefits from radiation-based thickness gauging for measuring the thickness of paper, cardboard, and various packaging material. Gauges enable manufacturers to maintain precise thickness control during production, ensuring uniformity and desired properties such as strength and flexibility. By maintaining consistent thickness, they achieve better printability, folding properties, and overall packaging quality. For example, to measure the thickness of a plastic film used for packaging, pharmaceutical packaging, and other flexible application. Precise thickness control ensure packaging integrity and barrier properties. In conclusion, there is still more applications that have been used thickness gauging using radiation in different sectors, such as medical and many more, which will be explained in detail in the next part. Its benefits of non-contact measurement, high accuracy, and rapid measurement speed, making it a valuable tool for ensuring quality control and a process optimization.
Hi! Now you are with me, Fatini, and I would like to share with you guys the benefits of thickness gauging using radiation. This radiation-based thickness gauge offers several benefits but I will just share 3 of them. First, non-destructive testing. It is a non-destructive testing method, meaning it does not change or harm the substance being measured. This permits measurements that are accurate and trustworthy without affecting the quality of the thing or structure. Second, high accuracy. It gives accurate measurements frequently with high degrees of precision. This makes them suitable for applications that require precise thickness control, such as manufacturing processes or quality control. Third, wide range of materials. It can be used on a wide range of materials, including metals, plastics, composites, and other materials. Due to how versatile they can be used in a variety of sectors, including the petrochemical, construction, automobile, and aerospace industries. Class, it is essential to remember that while radiation-based thickness gauging has many advantages, it should be carried out by qualified experts while following the right safety procedures to ensure the proper handling of radiation sources while decreasing potential risks. Now that you know the benefits of thickness gauging using radiation, let me explain the principle behind it. Beforehand, let me briefly explain the devices. There are various devices used for thickness gauging using radiation. The specific device depends on the type of radiation being used and the application requirements. Here are some common devices used for thickness gauging: X-ray thickness gauge, gamma ray thickness gauge, beta backscatter gauge, and last but not least, neutron gauge. These are just a few examples of devices used for thickness gauging using radiation. The choice of device depends on factors such as the type of radiation, the material being measured, the required accuracy, and safety considerations. But for today, we'll just focus on one device only, which is the first one, the X-ray thickness gauge. Now, let's dive deeper into the principal work. This is the X-ray thickness gauge in industry. I guarantee you can see nothing from this scene due to the radiation that we couldn't see with our naked eyes. So, here you go, the animated one. So how does it actually work? Here is a step-by-step explanation. Look at this flowchart. We have 6 important steps. First, X-ray source. Second, material under test. Third, attenuation of X-rays. Fourth, detector. Fifth, analysis. And last but not least, 6, thickness calculation. Now, by using this diagram, let's go one by one. First, X-ray source. The X-ray thickness gauge consists of an X-ray source which emits a beam of X-rays. The source is typically positioned on one side of the material being measured. Second, material under test. The material whose thickness needs to be measured is placed between the X-ray source and the detector. The X-ray passes through the material. Third, attenuation of X-rays. As the X-rays penetrate the material, they undergo attenuation. Attenuation occurs due to the absorption and scattering of X-rays by the atoms and electrons present in the material. The degree of attenuation is dependent on the material's density and thickness. Fourth, detector. To determine the strength of the transmitted X-rays, a detector is positioned on the material's reverse side. The detector could be a scintillation detector, a solid-state detector, or another appropriate X-ray detector. Fifth, analysis. The detector measures the intensity of the transmitted X-rays. This measured intensity is compared to the initial intensity of the X-ray beam emitted by the source. 6. Thickness calculation. The amount of X-ray attenuation can be calculated by comparing the differences in intensity. The thickness of the material and the attenuation level are correlated. In order to convert the measured intensity into thickness values, a calibration chart or mathematical model is used. The calibration process involves measuring material thickness using an X-ray source and detector setup and creating a reference curve or calibration chart. This relates the measured X-ray intensity to the corresponding thickness. By exposing unknown materials to the beam and analyzing the transmitted X-ray intensity, the material's thickness can be determined. Last from me, keep in mind that the implementation and components of an X-ray thickness gauge may vary depending on the device and application. Safety precautions and regulations for handling X-ray sources are also important considerations to ensure operator safety and compliance with radiation safety guidelines.
So, as what has been discussed, we know that thickness gauge is a measuring instrument that can be used to determine the thickness or gauge of a material. Because of its function in which help people in standardizing the thickness of material, it was widely used in manufacturing process.
So we are at the end of our presentation, and now I open the floor to ask the question if you have any question regarding the topic that I presented.